Hello everyone, I am Rishi. I'm going to explain you on the topic of quantum key distribution, the future of secure communication. Let me give you on a brief introduction on what is quantum key distribution. That is, let's start by framing the problem. At its heart, cryptography is the method we use to ensure secure communication over insecure public channels. We want to guarantee three things, that is confidentiality, integrity, and authenticity. But the cornerstone of all the secure communication isn't the encryption itself. It's the key exchange process. The moment two parties agree on a secret key, honestly, in our current digital world, this is handled by classical methods like RSA or the Diffie-Hellman key exchange. As you know, these systems are built upon the belief that certain mathematical problems are too difficult to solve in a reasonable amount of time. Specifically, they rely on the computational difficulty of factoring large numbers and solving discrete logarithms. This difficulty is what makes them secure. However, the security is only computational, meaning it is guaranteed only as long as our attackers' computers are fast enough. And that brings us to the imminent threat of quantum computing. Once a sufficiently powerful quantum computer exists, this mathematical barrier collapses entirely. This leads us directly to the need for a physically secure solution, quantum key distribution (QKD). It's a paradigm shift from math-based key exchange to physics-based one. Why we need QKD? Let me give you why we need QKD. Now let's spend a moment on why. Because this is the driving force behind the QKD research. The key threat is a quantum algorithm called Shor's algorithm. While a classic computer might take millennia to break a 2048-bit RSA key, the Shor's algorithm running on a powerful quantum machine could potentially do it in minutes or even in seconds. Think about the entire foundation of internet security, banking, government secrets, medical records could become instantly vulnerable. So the problem with classical cryptography is that it's based on a conjectured difficulty. We believe it's hard to break, but we can't mathematically prove it's possible. This is where QKD changes the game completely. It steps away from relying on computational hardness and instead uses the ironclad laws of quantum physics for its security. Executed by nature itself, this gives QKD what we call unconditional security, meaning the security is guaranteed regardless of the attacker's future computing power. Even if they had an infinitely powerful computer, they could not break the key without being caught. This physics guarantee this physical guarantee is the ultimate defense against the quantum apocalypse. Next, I'm going to tell you what is quantum key distribution. Let us understand what is quantum key distribution. QKD is a specialized technique for securely distributing a cryptographic key. It is not a method for sending encrypted messages. It only creates the key, which is then used with a classical algorithm like AES to encrypt the actual data. In QKD, two parties whom we call Alice and Bob. Alice, who is the sender, and Bob, who is the receiver, use a stream of individual quantum particles, typically photons, particles applied to exchange key information. These photons they travel through a dedicated medium called the quantum channel. This ingenious part is a mechanism for intrusion detection. If a third party Eve attempts to measure the key carrying photons, the fundamental rules of a quantum mechanics dictate that she will disrupt their state. This change in is physically instantly noticeable to Alice and Bob, acting as a built-in physical alias systems. QKD therefore provides both the secure key and a definitive way to verify that the channel was tamper-free during the exchange. Next, let me explain you what is qubits and polarization. To appreciate how QKD works, we need two quick concepts. First, the qubit or quantum bit. Unlike the classical bit, which is restricted to 0 or 1, the qubit can leverage superposition to exist in a combination of both states simultaneously. This expanded state space is what gives quantum systems their unique properties. Second, in QKD, we encode this quantum information onto the physical properties of the photon, specifically its polarization. Think of polarization as the angle at which light wave is oscillating. We use and we use two primary measurement system called bases. First would be rectilinear basis, the place basis. Here we encode 0 as vertical and 1 as horizontal. And 0 is vertical and the diagonal places, cross braces. Here we encode 0 as 45 degree and 1 as 135 degree. Each photon is carefully prepared to carry exactly one of the potential secret key using one of these four polarizations. This use of multiple non-orthogonal bases is the trick that prevents Eve from successfully copying the key. Next, let's go on for the BB84 protocol. The most famous and foundational protocol for QKD is the BB84 protocol, named after its creators Charles Bennett and Gilles Brasseur, who devised it in 1980. Let us break the 6 crucial steps proposed by the founders, where the magic of quantum mechanics truly kicks in. The first step would be key generation. Alice starts with two long, independent and random sequences of bits, zeros and ones, and sequence of bases, rectilinear or diagonal, that she will use to encode those bits. Second step would be quantum transmission. Alice prepares each photon according to her random bit and the random basis choices and sends them one by one to the quantum channel to Bob. Third would be measurement. Here's the key. Bob has no idea which basis Alice used. For example, for each incoming photon, he makes his own random choice, rectilinear or diagonal, to measure it. According to quantum law, if he chooses the wrong basis, this measurement result will be entirely random, often incorrect. If he chooses the correct basis, the measurement will be correct. The fourth step would be basic comparison. After all photons are sent, Alice and Bob switch to a public classical channel. They publicly announce which basis they use for each photon, but never the actual bit value. The fifth step would be key shifting. They then immediately discard all the bits where their bases did not match. They keep only the bits where both use the same basis, as they are now confident these bits are correct. This creates a shifted key. Sixth step would be error correction and privacy amplification. Finally, they compare a small random sample of the remaining shifted key to determine the error rate. A high error rate means he was listening and they discard the entire key. If the rate is low, they use classical post-processing techniques like privacy amplification to ensure the final shared secret key, which is private, perfect, and secure. The next would be detecting eavesdroppers. Let us focus again on the third eavesdropping detection because it's the protocol's greatest strength. The principle at work here is the Heisenberg uncertainty principle and the no cloning theorem. Eve cannot simply read the photon's polarization without disturbing it, and she certainly cannot perfectly copy it to read later. If Eve intercepts a photon, she must choose a measurement basis, if she guesses Alice's basis correctly, 50% of the time the state is fine. But if she guesses incorrectly, the other 50% of the time, her measurement forces the photon into a random state. When she resends this added photon to Bob, and Bob happens to choose the correct basis, he will receive an incorrect bit value. This introduction of detectable errors guarantees what we call tamper evidence. If the error rate is low, the key is good. If the error rate is high, the key is compromised, and the key exchange is immediately aborted. No information is ever compromised. Next, let me tell you about the role of the classical channels. It is important to clarify that QKD does not replace the entire internet. It works alongside a classical channel. The quantum channel is exclusively used for the secret key detection generation via photons. The classical channel, your standard public communication like, is used for all the metadata and the necessary coordination. This includes comparing their random bases, announcing their error checking results, performing the error correction and privacy amplification steps. The crucial point is here we have to remember is the secret key bits themselves are never ever transmitted over the classical channel. The key information is born in the quantum channel, and the classical channel merely helps them verify and process it, ensuring the final key is never exposed to classical interception. Next, let me tell you about the advantages and the limitations here. The advantages would be, starting with the advantages, would be ultimate security, built-in intrusion detection, and long-term confidentiality. Let me tell you guys about what is ultimate security. The defining feature is its unconditional security. Since the security is derived from the unchangeable laws of physics, it is future-proof against any advance in computing power. including future quantum computer. The second step would be built-in intrusion detection. The physical tamper evidence means that any key that is successfully shared is guaranteed to be a secret. If an attack occurs, the communication is simply aborted, providing complete peace of mind. Third step would be long-term confidentiality. Data encrypted with QKD derived key is protected for decades, making it ideal for information that must maintain secrecy over the long haul. Next, let me tell you guys about what is the limitations that researchers are looking hard to overcome even these days. First step would be specialized hardware. QKD requires extremely sensitive and complex equipment such as single photon detectors, which often need to be cooled to cryogenic temperatures and specialized laser sources. This makes the system extremely expensive and bulky. The second limitation would be limited range and speed. Photons get lost and attenuated in optical fiber. Currently, QKD links are limited to about 180 to 150 kilometers without an intermediate device called a trusted node. This limits its use to metropolitan areas unless you use satellite links. The third limitation would be integration challenge. Integrating these specialized quantum devices seamlessly into our massive existing standardized IT and telecom networks remains a significant hurdle in terms of cost and complexity. Next, let me tell you guys about what is let me tell you guys about real world applications used in QKD. QKD is no longer just theoretical. It's being deployed right now to protect what the industry calls the ground swells of data. One of the most spectacular examples is China's Meteor satellites, which was launched in 2016. It pioneered the use of satellite to ground QKD, successfully distributing keys over distance, thus exceeding 1,200 kilometers, effectively shattering the fiber optic distance barrier. On the ground, QKD is securing critical infrastructure. We see it protecting banking, transaction, military networks, and government communication lines for top secret data transfer across metropolitan cities. Furthermore, companies like Toshiba, IBM, and ID Quantic are actively commercializing the technology, building dedicated quantum secure metropolitan networks and devices. This transition from highly complex lab experiment to commercial rack mounted devices is a huge step towards QKD and everyday reality for high security applications. Next, let me tell you guys about the future of QKD. The trajectory for QKD is clear. More distance, more speed, and better integration. One of the biggest future trends is hybrid security. Since QKD is currently expensive and range limited, the industry is moving towards a system that combines QKD's physical security with the software-based projection of quantum post-quantum cryptography, which is PQC. This PQC. The layered approach is considered the safest and the most flexible transition energy. We are also seeing massive efforts to integrate QKD with modern networks, particularly 5G and secure cloud platforms to provide quantum level security to mobile devices and data centers. Finally, QKD is seen as a vital foundation for the ultimate goal, which is building the quantum internet. This network will use quantum repeaters and entanglement to connect quantum processes globally and enabling entirely new forms of secure communication and distributed quantum computing field is moving rapidly from pure research and practical deployment. Next, let me tell you guys about the conclusion, securing the digital future. To summarize our discussion, QKD is not just an upgrade to security, it's a revolution. It replaces the vulnerable mathematics-based system of today with a defense mechanism based on the unbreakable laws of physics. QKD guarantees that two parties can exchange an encryption key and instantly know if the key has been intercepted, if the key has been intercepted or not. Then QKD guarantees that two parties can exchange an encryption key and instantly know if key has been intercepted, providing a level of security that has never been possible before. As the threat of quantum computing looms, QKD is actively being deployed to safeguard our most critical communication links. It is the bridge we need to cross into the quantum era, ensuring our data remains secure, confidential, unbreakable. Unbreakable. Thank you very much for your time. I'm happy to take any questions if you guys have in this topic. I'm very happy to explain you a new topic on cryptography, which is quantum key distribution. I'm happy to share my knowledgeable insights.